Hi everybody, we'll get started in just a second here. Oh. I had an error there. I think it's okay. Alright, I think I fixed the issue. Let me turn the music down real quick. The stream might have been stuttering a bit there. I was grading, and apparently having Excel open uses up like all of my CPU power, which surprises me because it's just Excel. But now I shouldn't get the encoding overloaded error, and it should be streaming just fine. Let me know if there is an issue with the stream. Some brief announcements before we get started. So at the bottom there, you can see what's all due coming up. Make sure you're always checking that. Quiz 2 is due on Wednesday. Quiz 3 will be due on Monday. Quizzes 2 and 3 should auto-grade correctly. I don't believe that there are any issues with me having to go back and assign partial credit. There are some problems that it will specifically say, hey, here's a problem type that doesn't give partial credit. Make sure you do it correctly. I've made those worth like 1 point so that if you make a mistake, it's not a huge deal. And you get 2 tries anyway. What else? I graded Lab Worksheet 1. I pushed a button and it should have uploaded the files back to you. When you go into the assignment, there should be a comment left by me that says, please look at this file, or something like that. It just automatically generates that message. And then you can either open that file immediately, or you can upload it to Google Sheets and open it there. Anything that is in pink is an error that you need to look at. And all scores are on the left column, and your total score is at the top. And that total score should match what is in the gradebook. You can check the gradebook by looking at the Grades tab in Canvas to get your scores. Okay, so my computer looks like it's running normally now. My CPU is maxed out because of Excel. Ugh. So let's go ahead and get started. We're going to continue with our discussion of Chapter 4. We're going to talk about how to make ionic compounds today from moving around electrons. Hopefully you spent the weekend preparing a little bit of information with making Lewis structures, how to draw the dots around those elements, and how to form the correct ion. Remember that we're trying to match the octet rule by starting with the number of valence electrons that an element has based on its group, and then getting to 8 the fastest way, either by adding electrons to get to 8, or by removing electrons to get to 0, which then the next layer of electrons below that becomes the valence shell. Hopefully that all sounds familiar, because that's what we spent last Thursday doing. We're going to build upon that today to make ionic compounds. in more detail. So the first thing we want to talk about is that we know that ionic bonds form when you have a positively charged ion. I'm just going to draw up here. When you have a positively charged ion and a negatively charged ion next to each other, and they attract, and that makes your ionic bond. But it turns out that for neutral substances, there are no charges. We need to make the charges. So how do we do that? So for instance, if I just have sodium, which would not have any charge on it, and then chlorine, which would also not have any charge on it. I've written Cl2 here, but I'm just going to use one Cl here. How do I get the ionic bonds to form? And it turns out that we have to start shuffling electrons around. But the first thing I want to do is I want to show you this in action. And I don't remember if this is the right video, because for a long time I had a really bad video. I do have the right video here. Okay, good. So let me capture the YouTube video. And I want Lonnie. So heads up, there will be a really scary looking guy appearing on the screen right now. Yeah, he's a little bit creepy, but that's okay. So we're going to mute him. All right. And what Lonnie's going to do, Lonnie is going to demonstrate the reaction of sodium metal with chlorine gas. So these are not ions yet. These are substances that are in their elemental state. You can see right here in this chamber, it's very hard to see, but it's kind of yellow. And the yellow that's inside this chamber is chlorine gas. Chlorine gas is extremely deadly. If you breathe this, you will basically scorch your lungs and then be unable to breathe, and then you'd suffocate. Sodium metal, as we saw in one of our videos before, is explosive. You put it in water and it detonates. The sodium metal that we're going to use is stored in this bottle here, which is coated in mineral oil. And so he's going to take a chunk of it. He's going to put it in hexane, which is just to wash the mineral oil off. Hexane itself evaporates really quickly, so we'll replace it. So now he's going to take that sodium chunk, which you can see in the tongs right now. He's going to put it in a ladle. And in order for it to react with the chlorine gas, it needs to be hot. We're going to provide it some heat, thermal energy, in order to get it to start the reaction when it gets put in the chlorine. So he's heating it up. It's getting really hot. You can tell that it's starting to burn because of the orange flame. And then he's going to put it in the chlorine gas cylinder here. And then quickly shut it so he doesn't breathe it. And this is what happens. You can see the gas is kind of escaping through the little opening, but it's now getting sucked out through the vent. This vent down here is a very strong downward fan, so he's in no danger of breathing this. But what's going on inside this chamber is that the sodium metal is reacting with the chlorine and it's releasing a ton of energy. That's why it's glowing red hot. That reaction, or that heat evolution, causes the reaction to perpetuate. So more sodium will react with more chlorine. Eventually one of them runs out and then the reaction will stop. And you can see the ladle was red hot when it came out. That's how hot it got. And now if you let this settle down and condense, what you will have at the end is an ionic compound. Like, it's currently in the gaseous state. It's really hot. And it looks like this. He's prepared some earlier. And this is table salt. And you could actually take the table salt and put it on food and eat it. Now, I don't know why you'd want to do that in the laboratory, because that would be, like, unclean. And oh, Lonnie, what are you doing? Why do you have an egg? Why do you have an egg in the laboratory? Lonnie, you didn't wash your hands before you did the experiment. Oh, Lonnie, no. Oh, goodness. Well, what can you do? Alright. Hopefully he will be alright. But that's how we make sodium chloride from gaseous elements. Now you might ask yourself, well, where are all the gaseous elements around us? And the answer to that is, well, they reacted a long time ago. Back at the start of the quarter, I showed you, or I linked to you, the video about how elements came about. I don't know if people watched it. I couldn't air it because I know I would get a copyright strike. That is the History of the World, I guess, video. And it talked about how elements were formed in the cores of stars. And when stars explode, you get bigger elements. And when those elements combine and make stars, they explode and make bigger elements. And so on and so forth. Some of those possibilities that could have come out from a star exploding would be sodium and chlorine. And those would be the solid sodium and gaseous chlorine. Well, the instant those two contact each other, they would react like they did in the bottle that Lonnie was showing you. And thus, they would react and make sodium chloride, which then collects as the planet was forming, and then would eventually, billions of years later, be washed into the ocean or mined up from under the earth, and then we would eat it. So, the reaction that I showed you formed the ionic compound sodium chloride. In the ionic compound, we have ions, and those ions are shown with the charges when you separate them apart. But you'll notice that in the compound, the charges are not written. This is because instead they are implied. Okay? When you write an ionic compound, you can't write the charges in there. So writing something like this, where you just kind of sneak the charges in there, is wrong. Doing that is not the proper way to represent these compounds. So whenever you have an ionic compound, you want to write it with no charges present, because the charges have actually neutralized each other. The positive and the negative cancel out, and so the unit, the NaCl, doesn't have a charge overall. This is the reaction that's going on. Let me just do this, actually. When my sodium bonks into a chlorine, it becomes sodium chloride. And you'll notice here that this doesn't have a charge on it, neither does this. And then this over here doesn't have a charge because it's not a compound. But the charges are implied. So I actually did something like this. This became this. And this became that. Now, if I were to draw that as an electron diagram with a Lewis structure, I could see what's happening. And this is what's called an electron transfer, which is what's going on here. So when electron transfer occurs, something wants to pass its electrons to something else. In this instant, we have sodium, which is the metal. Metals don't want to keep their electrons. They want to ditch them so they can get closer to an octet. And nonmetals, like chlorine, want to accept them. So if we have both of those molecules right here, what we could do is take that lone electron on sodium and just go whoop. We'll just slide it right on over. Boop. So now what we're doing is we are predicting which ion will form twice. On Thursday's lecture last week, I gave you a sodium atom and I said, predict the ion. I gave you a chlorine atom. I said, predict the ion. Now your job is to predict which ions form for both of them, and then determine how many shuffles, or how many electrons, you got to move around, so that everyone involved has an octet. Now in this case, I only had to slide one electron, but in some ionic compounds I might have to slide more than one electron, or slide electrons to more than one thing. And we're going to see that in the examples that come up. Alright. Finally, once we have formed the ions will make the ionic bond, and that's what you are seeing in the chamber with the gaseous ions. We didn't have a way to fast forward that because it takes a long time. The stuff in there is thousands of degrees hot, and it takes a while for it to cool. So let's try and make some ionic compounds from here. I'm going to do the first few examples, and then I'm going to have you try them. So the first example I want to do, I got to do this. I'm going to do the top one up there, KBr, and then I'm going to do MgCl2, and then I'm going to have you try to do the other ones. So let's write the Lewis structure for potassium, first of all. So potassium is in group 1. Since it's in group 1, how many valence electrons would it have? And you would draw that many dots. Whoop, there you go. Then I do the same thing for bromine. Bromine is in group 17, or 7a. How many electrons does it have in its valence shell? And hopefully you have drawn the symbol for it. We put 1 dot per valence electron. And bromine would have 7. Now I have to move electrons around so that everyone has an octet. So I'm going to take this electron and it's got to go somewhere. Should it just go off on its own? Probably not. Where should it go? Oops, I'm on the wrong layer. Great. Hold on. Guess who didn't check the option when they started? It was, hint, it was me. Okay, hold on. Alright, there we go, that's better. Alright, where should this electron go? It should go right here into this empty space. So when I have done that, my potassium no longer has any electrons and has this charge. But remember, 0 valence electrons is like having 8, because the next layer down becomes the valence layer. Here's the original 7 that bromine had. And then this, which I'm drawing in a hollow circle here, is the extra one that potassium passed over. It's got 1 more electron than it started with, so now this is its charge. So I would form an ionic compound between potassium and bromide. Since I only had to pass 1 electron over to get everyone an octet, I only needed 1 of each element, so the ionic compound that I form is KBr. Now let's do magnesium chloride. So I'm going to have to work with magnesium and then chlorine. How many valence electrons does magnesium have? It has 2, because it's in group 2a. How many valence electrons does chlorine have? Well, it's got 7, because it's in group 7a, or 17. And now I just do the same thing. I got to pass my electrons over. So I'm going to pass 1 electron from magnesium to chlorine. So this guy's going to go right here. And that's going to fill chlorine's octet. But now I have an issue. And that issue is I have this extra electron here. Where does it go? Well, if I have extra electrons to pass around, I got to pass them with something. And I need to get another atom available to do that. So I'm going to find another chlorine. Because there are tons and tons of atoms everywhere. You're going to be able to find another one that you need if you're mixing these two things together. And I'm going to pass my second electron to it. So it has an octet now too. My chlorine has an octet. This chlorine has an octet. This chlorine, or this magnesium now has an octet because there are no valence electrons left, so the next layer down becomes the valence layer. I make this. Magnesium has a 2+ charge because I took away 2 of its electrons. And each of these chlorines has a -1 because each of them gained 1 electron. Now when I have to go write the formula, I say, okay, I took 1 magnesium and 2 chlorine. What's my formula? The formula is MgCl2. Another way to think about this is if you can get to the ions, then you can figure out what the formula of the substance is by just looking at it. How many minuses do I need to balance this 2+? I need 2 of them, so I need 2 chlorines to make magnesium chloride. That's the gist of how to do this. I'm going to let you try to do the other three. So the calcium oxide one, the sodium nitride one, and then finally the aluminum oxide. Some of these you may have to move around a lot of electrons. So give it a shot. I'll give you 5 minutes to try it, and we'll go over the answers in just a second. See you in a bit. Just another second or two to finish up your answer. Let me clear my diagram here. Oh, it didn't select all. Oh, because I drew that on the wrong layer. Okay. Oh, everything's terrible. Why is this a thing? Sorry, I'm fighting with Photoshop here. Hold on. There we go. Okay. Tiffany, did you post a link in the chat? Because I didn't see one. I think I can give you permission. I can't. It doesn't look like. Can you post it again? Unless you posted it like really early and I just didn't see it. We're going to go over the answers in a second. I just wanted to diagnose this problem here that was coming up. There we go. All right. So let's go over the answers here. Let's do calcium oxide first. Oops, I'm drawing in white. Hold on, that's not going to show up. That's not a pen. There you go. Calcium and oxygen. I might have it set to not putting links up. Can you send it to me in an email, and then during the break I can post it? Because I can post whatever link I want to. I think it might just be banning links because I don't want people coming in and spamming. But yeah, send me an email, and I will try and put it in there. Anyway, let's do calcium here. So calcium should have 2 valence electrons because it's in group 2A. Oxygen's in group 6A, so it's going to have 6 valence electrons. And then I'm going to pass one over here because I have a space to put it. And I'm going to put the other one in this space right here. Oxygen can take 2. Calcium's got 2. So now, when I make my ionic compound, I have calcium with a 2+ charge, and oxygen, which has 8 valence electrons now, with a 2- charge. And the formula ends up being I only needed 1 of each to satisfy the octet for everybody, so I just write CaO. Here's my sodium over here, and my nitrogen. Sodium's got 1 valence electron. Nitrogen's got 5. I need to put this electron right here. But now I need more for nitrogen. Nitrogen demands more electrons. So I gotta get another sodium here. I'll put this one right here. Oh, I need more sodium. We'll move this guy right there. And then we get na 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 na. No, that's not what we get. So this is what I have now. I have 3 of these sodium plus ions. Na 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 na. Get the Batman theme stuck in your head there. And I have an N with a 3- because it took Here were the 5 electrons it started with, and now it has 3 more. Sneak one in there. So I'd write its formula. There are 3 sodiums, so I go Na subscript 3, and a nitrogen. There you go. There's no space over there, so I gotta go down. Alright, last one, aluminum and oxygen. So aluminum's got 3 valence electrons, and oxygen has 6. So I can pass 2. That's not where I wanted that to go. There we go. And that'll give that oxygen an octet. But I still have an extra electron, so I need to find another oxygen to pass more electrons to. And I can do that. But now I'm out of aluminum electrons, and oxygen still needs an octet. Everything's got to have an octet, so it means I need another aluminum. So I'll pass this electron over. This oxygen is now okay. Let's put little check marks on the ones that are good. I need another oxygen. Oh, when does this end? And once we get to this point, I can move this electron here, this electron here, and now everybody has an octet, excuse me. So I made this aluminum with a 3+, because each one lost 3 electrons. I did that twice. For my oxygen, each of them gained 2 electrons. And now when I write my formula, I would write Al2 because there are 2 of those, O3 because there are 3 of them. Another thing that you'll notice is that all of the total charge cancels out. So I have 3+ and 3+ for a total of 6+. Over here I have 2 minus 2 minus 2 minus for a total of 6-. The total charge is 0. And this will always be true. You'll always have all of your charge cancel out in an ionic compound. If the charge doesn't cancel out, then you need to put more ions. If I had something that had a plus charge still sticking around, it would attract negative things to it, and the formula would then change. So, as a consequence of that, there will always only be one formula for a given ionic compound. And you can figure out that formula by using this method. Alright, back to the slide here. There's the homework practice for this section. Give me just a second to see here. I got the link here. So copy, paste. That looks good, and that should go through. Everybody should be able to see that. I mean, if you can't see it in the chat log, you can sure see it in the video. So there you go. So that is Tiffany's chemistry group Discord link. And if you get weird random people on there, because again, this is public, and anybody can access these videos if they see them, just boot them. You have my permission to kick them out. Obviously, don't kick out students, but, you know, and just like in real life, anyone who's an ass, you just kick them. Alright, so let's finalize this, because I've given you the groundwork on how to do ionic compounds. Now we can get to the point where we don't really have to draw the pictures at all. We can just use that knowledge and say, okay, this is how I get to those ions. Can I skip straight to the end? And the answer is yes. So once we know that the total charge of an ionic compound has to be 0, and we know what ions always form because we were just doing all this octet rule stuff, you can start doing it shorthanded. For example, what's the formula for the ionic salt that contains these 2 things? Well, if you have potassium and you make it an ion, you know it has 1 valence electron. So if I get rid of it, it'd become that. And if I have sulfur, you know sulfur has 6 valence electrons. It needs 2 more to get an octet, so it'd be that. Now I can just say, okay, I've got these pieces. do the charges balance? And the answer is, well, they don't. Positive and -2 don't balance out. Positive 1 plus -2 is -1. I need another positive to balance it out, so I would just do this. Now they balance out. And there's the formula. So once we have learned the theory behind this, we don't have to draw the pictures anymore. And so I can ask you questions like this. What's the formula for whatever? Here are the elements that are involved. So that's what you get to do. What's the formula for the ionic compound containing these two things? Now, there is a little trick in here. And I haven't explicitly mentioned this yet, but let's see if you can figure out the pattern for what you've done so far. So try and figure out the ionic compound for this. I'm going to go fill my water real quick because I need to be drinking more of it, apparently. And we'll go over the answer in just a second. All right, did we get the answer? No, he typed it in the chat, so I wasn't sure. Nope. I went and washed my hands, and now my hands are all wet, and I can't use the tablet. Because I don't know what a towel is, because I'm a heathen. All right, so what ions form for these? So baryon's in column 2. So it will form the ion 2+. Selenium is in column 6, which means it needs 2 more electrons to get to 8, so it'll be 2-. And so there's 2 possible ways to combine these. I could have written this, or I could have written this one. But which one's correct? Excuse me. Which one is the correct writing? Like, how do we do ionic compounds? Which one have we always been putting first so far? It turns out that we've been following a specific pattern, and you might not have realized it. One of these always goes first, and which one is it? Turns out the one that we always put first is the metal. So this one is not how we write it. This is the correct answer. Yep, so you put the positive piece first. And I kind of got stuck on my text there. That's okay. So you're always going to put the metal first. How about this one? You just did this one. So on the previous slide, you got Al2O3. So you know that that must be the right answer. And the way that you can see that is you could say, okay, well, aluminum makes positive 3. It has 3 valence electrons. Got to get them all out of there. Oxygen has 6 valence electrons. I got to give it 2 more. And then how many of each do I need? Well, 3 and 2 wouldn't cancel out. I would need more of this. Oh, that's too much negative. Oops, I forgot the L. And you just go back and forth until you have all the charges balance out, and you'll get the correct answer. So now what I want you to do is I want you to try and make ionic compounds from these combinations, but try to avoid drawing the pictures if you can. Now, if you can't do that and you need the pictures, go ahead and keep doing that. It's okay to do that to start, but it will save you a lot of time if you can get to this point and understand why you're doing it. So I'll give you 5 minutes to draw the ionic compounds for these. Not draw, but write the ionic compounds. And we'll go over the answers in just a second. All right, how are we doing? We got the answers? Try typing them in the chat. I realize you can't do subscripts. I don't know if you can hear her. She came to visit. Hi, Maya. I'm teaching. Hi, Maya. I'm teaching. All right, let's go over the answers before the cat jumps in my lap. So we got calcium. Calcium forms what ion? Well, if it's got 2 valence electrons, and you got to get rid of them because it's metal, it would make that. Chloride comes from chlorine. Chlorine has 7 valence electrons. We'll give it 1 more. I would need 2 of these, 2 negatives, to match up with the positive, so I would write this as my formula, CaCl2. For magnesium and oxygen, magnesium has a 2+ charge because it has 2 valence electrons. Got to get rid of them. Oxygen has 6 valence electrons. We'll give it 2 more to make it 8. There's its octet. And now we can make our ionic compound, MgO, because 1 of each will neutralize the charge. Sodium will be +1 because we've seen it plenty before. It has 1 valence electron. We get rid of it. Phosphorus has 5 valence electrons. We're going to give it 3 more to make it have an octet. And then, unfortunately, the formula isn't NaP, so we don't get to take a nap. But I need 3 sodiums to get enough positive charge to counter this, so that means I got to put a 3 right there. Na3P. Down here we have beef, Be and F. Let's see what formula we make. Beryllium is in column 2, group 2A, so it has 2 valence electrons. We're going to get rid of them to make it +2. Fluorine has 7 valence electrons. It just needs 1 more. My ionic compound is BeF2. And then for this last one, aluminum has 3 valence electrons. Let's ditch them all. Sulfur has 6 valence electrons. Let's give it 2 more. There's the formula. So that's how we make ionic compounds out of formulas. Given that we know what valence electrons they start with, the elements that is, and how to get to the octet from there so we can predict the ions. Homework practice is at the bottom because they don't follow the octet rule. So there's going to be either a way for me to just tell you the information or for you to predict the information. Now, a last bit about ionic compounds from the perspective of, hey, it's a bunch of ions coming together. Remember that they form bonds in all directions. If I make a sodium chloride unit, and the simplest unit is NaCl, where does that show up in the crystal? Well, it's right here, and I've circled it with red. The formula ends up being the simplest pattern that you can repeat to make the crystal lattice. And so the NaCl formula unit, I am simplifying this because it's a little more complicated than what I'm showing, but that single purple and green, I could copy and paste that over and over and over and over and over again to get the ionic compound. In reality, you would have to actually paste like a cube with parts of ions in it, and that's way more complicated than it needs to be for the purposes of this class. So for your understanding of what a formula unit is for an ionic compound, they aren't discrete NAs and Cls that are bonded to each other and don't interact at all. They instead form this huge ionic complex where everything interacts with everything else. But the pattern that we observe in there is repeating based on the formula we just solved for. So that's called a formula unit. A formula unit is essentially a molecule, in quotes, for an ionic compound. So this is an ionic molecule. It's not a molecule, though, because we would have called it that. But since people know what molecules are, you could think of it as this. And it's just one of many members in an ionic lattice family. All right. So to do this last section, which is involving nomenclature and naming stuff, we're going to have to devise some algorithms, is the word I'm looking for. When we come back from the break, we're going to learn a few naming algorithms, and we're also going to learn how to name stuff like compounds with, say, iron in it. And you might say, well, wait a second, we don't know how to figure out the charge on iron. And there will be a way to do that. And we're going to show how that works in just a little bit. But for now, I'm going to put the title card back up. Let me put the timer on in the break time menu. I got to do that. There we go. Oh, that was for last. Let's clear this. Ooh, I've beaten some of my best times. Yes, that's not at all what I care about. Okay, so I'll start the timer. I'll start the music. And I'll see you in just a little bit to go over naming. Whoops. I hit the button a little too early. Alright, welcome back. Oh, I gotta erase these. Alright, for the rest of the class, we're gonna talk about naming stuff. And we might get into a little bit of Chapter 5. We're doing pretty good. So, naming ionic compounds is not super difficult, but there are some sticking points that you have to be mindful of. The real problem with this section is going to come up when you get to... Why is my encoding overloaded? Hold on, just a second. I'm getting an error message again. Why is my CPU doing the thing? If you have an issue with the video being blurry, make sure you click at the bottom where it says, what is it supposed to say? Should be a little gear icon that says settings, and then set it to either 720p or 1080p. And that should be a little bit better. I don't see why my CPU thinks it's maxed out. It's not. I'll just leave this open. Okay. The issue that we're going to run into with naming stuff is that later on in Chapter 5, at the very end of that, we're going to learn how to name covalent compounds. And they follow a similar but not exactly the same scheme. And that's where everything kind of falls apart. People get the schemes mixed up. So, very important, when you are studying these rules, make sure that you memorize the details to the T. And don't just make assumptions. Because what we're going to find later on is that if you apply the rules for one compound to another, you get the wrong answer. And that's no good for anybody. Alright. I don't know. I must have tapped through a few slides here. I was trying to wipe something off of my pad, and I think it interpreted that as clicking. Okay. Ah! Why is this happening? I thought it disabled that. Alright. First thing we're going to do is we're going to define something as a binary compound. Binary compounds are any compound that contains only two types of elements. For instance, NaCl, there are two elements. The first one is sodium, and the second one's chlorine, or chloride. CO2, we got a carbon and oxygen. And this P4O10 thing, we've got P and O. There can only be two elements for it to be binary. The next thing that we're going to define is a binary ionic compound. And a binary ionic compound is also binary, so there's only two elements, but there is one critical thing. One of those elements is metal, the other element is nonmetal. Now, this is actually the definition of an ionic compound right there in yellow. If you have a compound where you've got a metal and nonmetals bonding, you are working with an ionic compound. There are one or two exceptions that we'll talk about later when we get to talking about polyatomic ions. But for the most part, if you see a metal, you immediately know that you have a metallic, or you have an ionic compound. So let's look at some of these examples. So is KBr both binary and ionic? So let's look to see if it's binary first. So the first thing we'll look at is, does it have two elements or not two? So there's a K and there's a Br, that's two, so it is binary. So this checks out. The second thing to check is it ionic? So does it contain a metal? Here's my metal. Does it contain a nonmetal? Here's the nonmetal. This checks out too. So this is a binary ionic compound. Now, the reason that we're going over this is because this is going to be the first question that you ask yourself when you are naming a substance. Is it binary and is it ionic? If it isn't, you cannot use the naming rules we're going to talk about today. So here are a bunch of compounds, and just really briefly, note down on your paper if they are binary ionic compounds or not binary ionic compounds. And again, if it's blurry, click on the settings little gear icon in the video window and change the resolution. Because what might be happening is that my computer might be dropping frames on occasion, and then when your server sees that, it says, oh, it can't download this, I'm going to downgrade to a lower frame rate. And it might take a second, it might have to refresh it, but it should go back to normal. So hopefully you've looked through these compounds and you've realized, oh, they're all binary, but which ones are binary ionic? And remember, you got to look for metals. So here's a metal, here's a metal, here's a metal. So these are going to be my binary ionic. In H2O, there aren't any metals, and in SO3, there are not any metals. Those are not binary ionic compounds. They're just binary. So that's going to be the first question you ask whenever you are tasked with giving something appropriate names. Is it binary ionic? If it is, you're going to use the rules today. If it's not, you're going to use different rules in Chapter 5, and we'll get to those at that time. So let's name stuff. Now, knowing my students in the past, they like to name things by just listing off all the letters. Oh, it's NABR. Oh, it's NaCl. I do that too, because it's just convenient and you can read it that way. But we can't do that all of the time. For instance, if you are in a capacity where you need to identify compounds by proper names, and those compounds are sold in bottles that have to have specific labeling that specifies what it is, then those substances may have names printed on them that aren't just the letters written out. They might not write the formulas. They might write like sodium iodate or potassium chloride or whatever. In those cases, you got to know what those names are and be able to translate them to a formula or the reverse. And so here's the algorithm for naming things. This actually looks a lot simpler than it is. There's going to be a little bit of information that we're going to deal with in each of the boxes. But the first thing I want to point out is name the metal. You already know what all the names of all the metals are. This is just straight off the periodic table, with some exceptions. The part where we're naming the non-metal, this is the part that is new for a lot of people. And you might have heard me say chlorine or chloride, and I try to be very careful about what I'm saying, but sometimes it just slips out and I say the wrong thing or whatever. And it hasn't mattered up until this point. But now it does. It turns out that nonmetals, when they are ionic, have special names, and that name is we put "ide" on the end. And we'll talk about that in just a second. So again, metal names just come straight off the periodic table. And if the elements are in group 1A or 2A, or you're looking at aluminum, then all you do is write its name. And those are the names off the periodic table, no problem. Now, depending on what periodic table you're using, for example, I have a British periodic table, because apparently Web Elements is British. And they spell aluminium with an extra I in it. And they do the same thing with cesium. They put an A in it because Caesar, the way his name is spelled was Caesar, and that's what cesium is named after. But Americans trim out some of those letters, and that's perfectly fine. But we just have to be mindful of that when we're typing in names into something. Now, what if the metal is some other metal? So, for example, a transition metal, or maybe like uranium or lanthanide or whatever. Those metals do not have what is known as fixed charges. So these elements that I've shown on the screen here in yellow, 1A, 2A, or aluminum, have fixed charges. What that means is that they follow the octet rule. And if something follows the octet rule, then you know how many valence electrons it starts with and how many it will end with, which is 8, and the difference between those. That will lead you to a fixed charge. For example, sodium will always be +1 because it has 1 valence electron. Barium will always be +2 because it has 2 valence electrons, and you're getting rid of them both in each case. But what happens when we get to things like transition metals? They don't follow the octet rule, so we need to be more specific because we don't know their charge based on their name. Here's how we indicate that. If I give you a transition metal, so any other metal... Oh, you know what? Hold on. Let me get a different color here. Oh. Had the wrong pen selected. There we go. So any other metal that is not in groups 1A, 2A, or is aluminum is going to have a charge that I have to tell you about, or you have to solve for using math. And you will see what I mean by that in just a little bit. And so what that means is that if I say give you... I don't know where my cursor is. There it is. If I say give you this, then what I do is I go look up the name of this, which is chromium. And then I take the charge, and in parentheses, I write the charge as Roman numerals. So this becomes chromium 4. Here I do the same thing. Here's the 2 for my iron 2 plus. It goes right there. Here's platinum's 4 plus. It goes right there. So you have to look up the name, and you have to look up the charge of the ion based on the information I told you in the problem, or using other ways to solve for it. And again, we'll get to that later. Naming nonmetals is pretty much just the name off the periodic table, but you chop off a few letters and you type "ide" at the end. In your textbook, Table 4.2 has a bunch of elements that have "ide" on them, and we only ever use "ide" when we're talking about the anion form. So the "ide" name is reserved for ions only. Okay, and so that's what this is right here. And I'll highlight the charge. There we go. Oh. Pressed too much and it tried to click it. So elements off the periodic table that are not charged, they are in their neutral state, have their default name. But if they are a non-metal and they are an anion, then we give them "ide." And so there's a bunch of "ide" stems that you have probably already heard. So like nitride, oxide, chloride, fluoride, bromide, iodide, that sort of thing. The last step in naming something is to just simply drop the names that we gave these things in the box. So let's do that. So I want you to type in the chat what the name of this is without looking at the slide. Like your printout of the slide was what I mean. Try and name this and type it in the chat. First, look up the name of the metal. Then look up the name of the non-metal and give it an "ide." All right, I got one answer. Let's take a guess. Let's see here. So K is potassium, so I would write potassium down. And then Br is bromine. But I'm not going to do that. I'm going to put the "ide" on the end to get potassium bromide. And that's right. Now, the only comment I would make is that elements are not proper nouns. So every time you write the name of an element, it should always be lowercase. That's just in case, like, the Canvas program is case sensitive, and some of the questions are. Like, if I give you a blank field and say type in the name of this, and you put a capital letter, it might actually mark it wrong. So just be mindful of that. Now, here I capitalized it because it's the start of a sentence, and really it should be capitalized. So this P right here should actually be a lowercase p. I think that's just Google, or not Google, but Microsoft trying to capitalize my letters when I type sentences. All right, well, what I named this one? What's the name of this substance? Type it in the chat. In fact, we can make it like a typing game. Type it as fast as you can. Go, go, go. Oh, now I've got everybody participating. Yay. So let's write out the name. So Na is sodium. It's in group 1A, which is one of the names that we just write by itself. And then O is oxygen, but we change the end to oxide. There you go. That's the right answer. Sodium oxide. Now you'll notice here that nowhere in the rule does it say to do anything with this number. And so we ignore the quantities when we are dealing with ionic compounds. Okay, so be mindful of that. Don't put like disodium, because that would be wrong. We do not worry about how many numbers there are. We just name the metal and then name the nonmetal with "ide." All right. Let's do this example. Let's start putting in some transition metals. What formula would form from these ions, and then what would you name the compound? So now you have to synthesize the information that we learned before. So how do I make an ionic compound out of these two things? And then what would you call it? So write in the formula in the chat, and then give it a name. And remember, you don't want to capitalize it. I know it's weird not to capitalize things, but... So there's a name. What's the formula? Give that 2. There you go. That's right. So how do I get COCl2 from these ions? And we're going to do basically the same thing that we did before. So here's my cobalt with its +2. And here's my chloride. I need another one to match the +2 over here, so this will be my formula. And then to name it, I just need to name the ions that are present. So I would call this cobalt 2. Chloride. There you go. Now, something to note, the convention is that we don't put a space between the number and the word. So on Canvas, when it's grading you, I will actually mention that. I will say do not enter a space between the name and the Roman numerals in parentheses. So you'd want to type the word cobalt, don't hit a space, just hit an open parenthesis, type II, close parenthesis, and that would be the name. That is just how it's done. I know that that's frustrating and kind of pedantic, but chemists are jerks. Oops, I wrote through my thing, but there you go. That's the name. Here's another one for you. What would the name and formula be this? Oh, so how do I know the cobalt is 2? I have to tell you that. So I have to say, okay, you're working with this substance. So in this example, manganese could be any number it wants to be. But specifically for this compound that I'm working with, I am telling you that it is +2. Now for this one, actually, we're going to work backwards after we've solved the answer. And I'm going to show you how you calculate what the substance is, the ion is, from the formula. So do the same thing. Make a formula out of this, and then tell me its name. Oh, now be careful. One of those is different than the other. Which is it? Is it magnesium or is it manganese? That's why I'm giving this examples, because that's a common mistake to make. So these ions balance out. And so the formula I would write would be MnO. And then the name of this would be manganese 2. Oxide. Now, 2 things before we continue. First of all, does everyone know the Roman numerals up to 8? If you don't, I'm going to put on the slide. Oops, I didn't clear that. Oop. We're going to write these out really quickly, just so everybody has them. So Roman numerals aren't very common. You really only use them in 3 places. 1 is the Super Bowl, 2 is Final Fantasy games, and 3 is naming ionic compounds. I mean, I'm sure there are other uses for them, but... The Arabic numbering system is the system that we use today, and it is awesome, because it is base 10. And I'll go up to 10, because that's easy now. The Roman numeral system is kind of base 5, which is really stupid. Because then you have all sorts of crazy things you have to do subtraction and stuff, and it's obnoxious. So here's how Roman numerals. Look, so the first one's I. The second one is II. The third one is III. And then IV. 5 is V. 6 is VI. 7 is VII. 8 is VIII. 9 is IX. And 10 is X. Now, you don't need the top and bottom bars over them if you don't want to. So if you're just writing them like this, that's totally fine. It's just that you will see them in both ways, so just be mindful of that. So those are the first 10 Roman numerals. Other numerals exist. There is a method to this madness. What they are trying to do is that when you get to 1 before a new unit, you put a unit before it to represent subtraction. So this IV means 5 minus 1 because the 1 is in front. Whereas this down here means 5 plus 1. Minuses come before. Pluses come after. And if that sounds really confusing and stupid, why do you think the Roman Empire fell? Oh yeah, offended historians in one statement. Alright, so there's the formula, MnO, and the name is manganese 2 oxide. Let's suppose I gave you a different compound, though. Let's say I gave you this ionic compound, and I said, what ions form from this? Now, this is actually a little bit trickier to do, and so what we have to do is first we got to write out all the pieces. So I have 4 oops, that's the wrong pen. I have 4 oxygen atoms that are in their ionic form in this ionic compound. And so what this means is that everything has a charge associated with it in an ionic compound. And so all these boxes that I am putting here have charges that go in them. Now, some of these charges are going to be known. For example, oxygen, you know what oxygen forms as an ionic compound because it's in group 6A. It's a nonmetal, and it always follows the octet rule. So you know that the charge on oxygen is always going to be this. Because it has to be, right? It's an ionic compound. Now, the question is, what number do I put in this blank so that the whole thing has a total charge of 0? Well, if I sum all these charges together, I get 8 minus. And I got to put something in this blank here so that when I add them together, the total charge is 0. And there's really only one number you can do, and that's 8 plus. So this number that went in here would be 8 plus. And now we can give it a name because this is manganese with an 8 plus. I can call it manganese 8. And then this has got O2 minus. It's just oxide. So this would be called manganese 8 oxide. And you can see how this is different from manganese 2 oxide because I got a different formula. So when you are given a formula and you have to turn it into a name, you have to identify the charge on any transition metals by working backwards. And so you will always know the anion part because I'm only going to give you anions that follow the octet rule. From that information, you can then figure out what the charge is on the metal with a variable charge, put that number in, and then give it a correct name using Roman numerals. So for the first examples that I have here, there are no transition metals in here at all. What I want you to do is I want you to name these compounds So the top stuff, give it a name, find out what ion it is, give it the proper name, and then you got to go in the reverse direction. You got to turn the names into formulas by writing down, well, what is strontium? Okay, I got to find it on the table. What column is it in? What ion will it make? That sort of thing. Then put it all together. So do this. I'll give you 5 minutes to do it. Type your answers in the chat when you got it. We'll go over the answers in just a second, and then we'll do the next set, which has got transition metals in it. Okay? Good luck. We're all counting on you, and I'll see you in a bit. How about I put the examples on the screen? You guys are just praising me, and then I'm just not showing you anything here. I just realized that that means that my example that I did on the previous slide. So hold on, let me go back really quickly. So this example right here, you didn't even get to see any of it. Let me do it again. My fault. So let me show you again how we would do this. So you probably heard me talking about it. How do I name this? So here's my ionic compound. I don't know what the charges are on any of these things, but I do know I got 4 oxygen that are ions in an ionic compound. Ah! Slides, why? Ugh. Technical difficulties. Okay, why isn't it working? Now I'm really angry. Stop being stupid. Why is nothing... There, okay. Sorry. Alright. I have 4 ions of oxygen, and we know that all of the oxygen ions make a charge of 2 minus because oxygen is in group 6. It has 6 valence electrons. I need to give each one 2 more electrons to have an octet. So now I have to figure out what goes in this spot right here. Well, if I have 8 minus from negatives from oxygen, what do I need to balance that out? It must be this from manganese. So that's how we get manganese 8. And then oxide. So I apologize for that not showing up the first time. Oh, that's not what I meant to do. I meant to go over here and put this back on the board. So now you can do these problems. So now I can take a second to get more water. And we'll go over the answers in just a bit. All right, how are we doing on these? Nobody typed any answers in the chat yet, so I didn't know. I thought I would check up on you. So to do the formula part down here at the bottom, let me click on the right screen first of all. Try writing the formula for just these things, but make sure you're doing ions. So for example, what's strontium as an ion? So you got to find it on the periodic table and then give it the right charge. What's bromide on the periodic table? You got to find it and give it the right charge, and then put them together like you did before. Try that. I'll give you a few more seconds to do it. We'll go over the answers in just a second. All right, let's go over the answers here. So I want to name this thing, and I want to name this thing. These are all elements in columns 1, 2, or they are aluminum, so I just take their names. So this is lithium. And then this O is oxygen with ide on it. So lithium oxide would be the name for the first one. For this, I look up Be, and that's beryllium. Cl is chlorine. With an ide, it becomes chloride. Beryllium chloride. Al is aluminum. We already did oxygen. It's oxide in an ionic compound. And there's the name of the potassium iodide compound. No problems there, I imagine. So down here is where it gets a little more tricky. So I need to figure out what strontium looks like as an ion. So I had to go backwards here. So I know that this is the symbol. And now I got to find out what charge it is, which means I got to do the whole valence electrons, get to the octet thing. And you should have gotten that. Bromide is Br, and it's an anion, so you got to figure out what its charge, and you should be able to get to there. And then putting those two together, you should get this as your formula, because I do need a second one of bromide to match up the 2 plus charge. Here's the symbol for rubidium. It's in column 1, so this is the ion it must form. Here's nitrogen, but as nitride, I need to make it have an octet. Got to give it 3 more electrons. Rb3N is the formula. So this is basically the culmination of everything we've done in Chapter 4. Can you put it all together? And if you're struggling with it, then what that means is you got to go back to the earlier sections and develop the technique to get to this part. Because once you can write that down, you can get to this part no problem, because that's what we did earlier today. So sodium, what ion does it form? It forms plus. Sulfide, what ion does it form? 2 minus. I can make the ionic compound. Magnesium, what ion does it form? It's this. Iodide, what ion does it form? It's that. I can make the ionic compound. So that is how you create formulas out of names. And it's tricky at first, but eventually we'll get to the point where it's no problem. Now, what I want you to do is, we're out of time for the day, so on the next slide is the exact same thing, except you need to use ionic compounds that involve transition metals. So I want you to try these, and we're going to start on this slide on Thursday, and then we'll continue the polyatomic ions, and we'll finish Chapter 4. So we're going to do the rest of Chapter 4 on Thursday. We'll start Chapter 5. Excuse me. And we'll keep on trucking. We're almost to halfway through the material at this point. So I want to thank everyone for coming out. If you have any questions, let me know. Tomorrow is a Q&A. I do need you to send me questions if you have them. I will be here regardless. We might just start and then answer a few questions and then stop. But anything is fair game. You can ask me about Lab 2. You can ask me about the material. We do practice problems. You just have to suggest something for me to do and actually have it for me. But yeah. I will catch everybody tomorrow for that. Again, there's the due dates at the bottom to be mindful of. There is a quiz due tomorrow. Make sure to do that. Thanks for watching, and I'll see you next time.